welcome to True Projects. In this video, we are going to explain about the project entitled as Enhancing Breast Cancer Diagnosis with Bidirectional Recurrent Neural Networks, a novel approach for histopathological image multi-classification. So before getting into the video, let me give you the brief description about the project. This project focuses on improving breast cancer diagnosis by applying bidirectional recurrent neural networks to histopathological image analysis. The approach leverages both forward and backward contextual learning to capture complex tissue patterns within medical images by enabling effective multi-class classification. The system aims to accurately distinguish between different breast cancer subtypes. This method supports more reliable and automated diagnostic decision making in clinical practice. Coming to the abstract explains that diagnosing breast cancer using histopathological images is difficult because breast tissue images contain complex structures and very subtle differences between cancer types, which can easily lead to errors. Manual analysis by pathologists not only takes a lot of time but can also vary depending on individual expertise. To address these challenges, the project proposes a deep learning based solution using bidirectional recurrent neural networks for multi class classification of breast cancer images. By learning image features in both forward and backward directions, the model captures richer contextual and spatial information from tissue samples. This approach enhances classification accuracy across different breast cancer subtypes and serves as an effective computer aided diagnostic tool to support pathologists in making more consistent and reliable decisions. Coming to the existing system explains highlights that traditional breast cancer diagnosis methods mainly depends on convolutional images processing and machine learning techniques such as SVM, KNN and random forest, which uses handcraft features like texture, shape and color. Although newer methods employ convolutional neural networks to automatically extract features, they generally process histopathological images as a static input. As a result, these systems are unable to capture important contextual relationship between different spatial regions of the tissues. This shortcomings often causes misclassification, particularly in multi-class classification tasks where fine structural variations are important. Moreover, existing approaches usually require heavy pre-processing and show limited ability to generalize across different data sets. Coming to the proposed system or base paper work, the proposed system explains a deep learning based framework that combines convolutional neural network and bidirectional recurrent neural networks to improve breast cancer histopathological image classification. In this approach, CNN are used to automatically extract meaningful deep features from the images, which are then arranged as sequence and fed into a bi-RNN. By processing the feature sequence in both forward and backward directions, the biRNN effectively captures contextual and spatial relationship within tissue patterns. This enhances the model's ability to distinguish between multi breast cancer classes with greater accuracy and robustness. Overall, the system minimizes dependency on handcrafted features, ensuring consistent diagnostic results and serves as a reliable decision support tool for early and precise breast cancer detection. Coming to the data set, the Break His Breast Cancer Histopathological Dataset is a comprehensive and widely recognized dataset used for research in automated breast cancer diagnosis. It contains 7,909 high resolution RGB histopathological images collected from 82 different patients, ensuring diversity in tissue samples. All images are stained with hemotoxylin and eosin, a standard staining technique that highlights cellular and tissue structure important for cancer analysis. The dataset includes image captured at four different magnification levels, that is 40x, 100x, 200x, and 400x, which allows models to learn both coarse and fine grained tissue features across multiple scales. The images are categorized into two main classes. Benign is of 2480 images and malignant is of 5429 images. with further subdivision into multiple tumor subtypes, making the dataset suitable for both binary and multi-class classification tasks. Due to its detailed annotations, varied magnifications, and real-world clinical relevance, the Break-His dataset is highly valuable for developing, training, and evaluating machine learning and deep learning models for accurate breast cancer detection and classification. Coming to the novelty or extension or enhancement or improvement. As an extension to the classification system, models from the YOLO family were implemented to detect and localize abnormal regions within histopathological images. YOLO enables fast and accurate object detection by identifying suspicious cancerous areas in a single forward pass, helping in precise localization of tumor regions rather than only image level classification. To improve more transparency and trust, the explainable AI technique GradCam was applied. GradCam generates heat map that highlights the regions of the images that most influence the model's prediction. This helps pathologists understand the model's decision making process and verify whether predictions are based on clinically relevant features. Furthermore, in addition to the model enhancements, a user friendly web interface was developed using the Flask framework. This interface allows users to upload histopathological images and obtain real time predictions from the trained model. The Flask based system makes the solution more accessible and practical for real world use by enabling easy interaction without requiring technical expertise. Coming to the flow of the work, first we need to import the packages. The workflow begins with importing all the required libraries and framework necessary for image processing, deep learning, model training, evaluation, and web deployment. It includes packages for data handling, image augmentation, neural network modeling, evaluation metrics, YOLO based detection, and Flask for building the web application. Proper environment setup ensures smooth execution of all subsequent modules. Next, data preparation. In this module, the breast cancer histopathological dataset is collected and organized for both binary and multi-class classification tasks. The dataset includes image captured at four different magnification levels: 40x, 100x, 200x, and 400x to capture tissue details at various scales. Separate datasets are maintained for classification and detection tasks to support parallel learning objectives. Next, pre-processing. Pre-processing is performed differently for classification and detection tasks. For classification, image data augmentation techniques such as resizing images to 299 into 292, random horizontal and vertical flipping rotation, color jittering, normalization, and tensor conversation using torch vision transformer are applied to improve model generalization. For detection, all relevant datasets are merged into a single dataset and a data.yaml file is created for YOLO models containing image paths and class label definitions. Next, parallel dataset management. This module ensures the maintenance of two parallel input pipelines. The classification pipeline uses images along with their corresponding class labels, while the YOLO detection pipeline uses image paired with bounding box annotations and class information. The separation allows independent yet coordinate training of classification and detection model. Next, model training. In this stage, multiple classification models are trained on all four magnificent datasets for both binary and multi-class classification. Baseline models such as VGG19, AlexNet, DenseNet, BRNN, BRNN plus GRU, and BRNN plus GRU plus FLOP are evaluated, followed by training the proposed model BRNN plus GRU plus FLOP plus ADA grade for improved performance. As an extension, YOLO based detection model, including YOLO V5, YOLO V8, YOLO V9, and YOLO V11, are trained to detect and localize cancerous regions and identify their respective classes. Next, model evaluation. The trained models are evaluated using appropriate performance metrics. Classification models are assessed using accuracy, precision, recall, FN score, confusion matrix, and ROC curves to measure prediction reliability. Euro detection models are evaluated using mean average precision, and recall, and different YOLO versions are compared to identify the best performing detection model. Next, interface pipeline. This module integrates the trained model into an interface pipeline using the Flask framework. When an image is provided as input, the YOLO detection model is executed first to localize suspicious regions and draw bounding boxes. The detected regions are then passed to the best performing classification model to determine the cancer type accurately. Next, Flask Web App. The final module focuses on deploying the system as a web application. The front end is developed using HTML that allows users to upload histopathological image easily. The Flask backend processes the uploaded image to run detection and classification models sequentially. The results are then displayed to the user, showing the image with bounding boxes, predicted cancer class, and confidence score, making the system practical and user friendly for real world applications. The algorithms used are baseline models VGG19, AlexNet, DenseNet, BRNN plus GRU, BRNN, BRNN plus GRU plus FLOP, and proposed models are BRNN plus GRU plus FLOP plus ADA grade, and as an extension YOLO based detection models we have used YOLO V5, YOLO V8, YOLO V9 and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. IPYNB files. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This is a database file used to store the user information. Coming to the execution of the project, firstly, you need to copy the code folder path from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. In the Anaconda prompt, this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally with the default address and the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. So now the home page of the project should be displayed in the browser. This is a front end built using the Flask framework. In this page, we have home button and register button. Click on register button so that the create account form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and the login.html page will be opened where you need to enter the username and password to log in the application. Then click on sign in so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and sign out button. Firstly, click on prediction button. As we are dealing with both classification and detection, both the things are being displayed. Firstly, let us check with classification. When you click on classification, Here, the classification process form will be open where you need to upload the file and then predict the classification. First, choose the file. The image has been successfully uploaded. Then click on Start Classification so that the given image is pre-processed and the output will be displayed as the analysis summary is given below, like the binary classification. It is defined as benign. The confidence level is of 89.31%. And multi-class classification, it is defined as adenosis. The confidence level is of 96.12%. Here we have the image analysis, like the original image and the GradCam heat map image. And we also have the recommendations, safety precautions, and next steps. And below we have the actions, like if you click on new analysis, again the form will be open. We can print the report or share the details, view the graphs, or try detection. Now let us click on new analysis and let us give an other image. The image has been successfully uploaded, and click on Start Classification so that the given image is pre-processed and the output will be displayed. Like the diagnosis results are given below. The analysis summary, the binary classification is malignant, confidence score is of 89.88%, and multi-class classification is ductal carcinoma. The confidence is of 93.29%. And we also have the image analysis, like the original image and GradCam heat map image. And here we have the recommendations, safety precautions, and next steps. Now click on new analysis where you need to upload another image for classification process. The image has been uploaded. Then click on Start Classification so that the given image is pre-processed and the output will be displayed. The diagnosis, the diagnosed results. The results are analysis summary, binary classification is malignant, multi-class classification is fibroadenoma. The confidence is of 92.81%. And we also have the image analysis, like the original image and GradCam heat map image. We have the recommendations, safety precautions, and next steps. Click on new analysis. Again, upload another image. The image has been uploaded. Click on classification for the output, and the results are displayed like binary classification is malignant, multi-class classification is ductal carcinoma. We also have the confidence scores given below, and the image analysis, like the original image or GradCam heat map image. Now, as we have seen with classification, now let us check for detection. When you click on the detection button, the detection form will be opened where you need to upload the image and click on the start detection. The detection image has been successfully uploaded, and start the detection process so that the output will be displayed like the detection summary for binary classification, like annotated detection results are benign. It's clearly showing along with the bounding boxes. And here we have multi-class detection with the bounding boxes. We also have the detection information, like detection method, region localization, and visual analysis. Now click on graphs button so that classification graphs and detection graphs will be displayed. So let us check one by one, first with classification graphs. When you click on classification graphs, the histopathological image analysis breast cancer multi-classification graphs will be opened. Here we have 40x, 100x, 200x, and 400x. Let us check one by one. First, 40x graphs. In this first, we have confusion matrix graph. The confusion matrix shows that the model correctly classified 178 benign and 418 malignant samples, indicating very high classification accuracy. Only two benign cases were misclassified as malignant, and no malignant cases were incorrectly predicted as benign, demonstrating strong reliability in cancer detection. Next, we have ROC curve graph. The ROC curve shows that the BRNN-GRU model achieves an AUC value of 1.0%, indicating perfect classification performance. This means the model effectively distinguishes between benign and malignant cases, where zero trade-off between true positives and false positives. Next, we have accuracy by model graph. The graph compares the accuracy of different models, showing that the proposed BRNN-GRU flop ADA-GRAD model achieves the highest accuracy among all approaches. Overall, hybrid BRNN-based models outperform traditional CNN architectures, highlighting the effectiveness of bidirectional sequence learning for breast cancer classification. Next, we have precision by model graph. The precision comparison shows that the proposed BRNN GRU flop ADA grade model achieves the highest precision, indicating very few false positive predictions. Overall, BRNN based hybrid models demonstrate better reliability in correctly identifying cancer classes compared to traditional CNN models. Next, we have recall by model graph. The recall comparison indicates that the BRNNGRU and the proposed BRNNGRU flop ADA grade model achieves the highest recall, meaning they successfully identify almost all actual cancer cases. This demonstrates the model's strong ability to minimize false negatives, which is crucial for reliable breast cancer diagnosis. Next, we have F1 score by model graph. The F1 score comparison shows that the proposed BRNNGRU flop ADA grade model achieves the highest balanced performance among all models. This indicates an optimal trade off between precision and recall, making it the most reliable model for breast cancer classification. Now, let us check with 100x graphs. In this first, we have confusion matrix. The confusion matrix shows that the VGG19 model correctly classifies most histopathological images across multiple breast cancer subtypes with high accuracy along the diagonal. However, some misclassification occurs between visually similar classes such as ductal carcinoma and lobar carcinoma, indicating limitations in distinguishing subtle tissues variations. Next, we have ROC curve graph. The ROC curves indicates that the VGG19 model achieves high AUC values for all breast cancer classes, demonstrating strong multi-class discrimination capability. Both micro and macro average AUC values close to 0.99 confirm the model overall effectiveness in distinguish between different histopathological tumor types. Next, we have accuracy by model graph. The graph shows that VGG19 achieves the highest accuracy among the baseline models, followed closely by AlexNet and DenseNet. The proposed BRNN-GRU flop ADA grade model significantly improves accuracy compared to other BRNN variants, demonstrating the effectiveness of the enhanced architecture. Next, we have precision by model graph. The precision graph shows that VGG19 achieves the highest precision among baseline models, indicating fewer false positive predictions. The proposed BRNN-GRU flop ADA grade model significantly improves precision compared to other BRNN variants, demonstrating better reliability in classification. Next, we have recall by model graph. The graph compares recall scores across different ML models, showing that VGG19 and AlexNet achieves the highest recall, while BRNN and BRNN-GRU flop perform the worst. Overall, CNN-based model outperforms recurrent and hybrid models with BRNN-GRU flop ADA grade offering a moderate improvement among the hybrids. Next, we have F1 score by model graph. The graph shows that VGG19 and AlexNet achieve the highest F1 scores, indicating the best balance between precision and recall. BRNN based model performs significantly worse through BRNN-GRU flop ADA grade shows noticeably improvement over basic BRNN variants. Next, let us check with 200x graphs. In this first, we have confusion matrix. The confusion matrix shows that the model correctly classifies most cases with 172 benign and 424 malignant predictions made accurately. Only a few misclassification occurs, indicating strong overall performance. Next, we have ROC curve graph. This ROC curve shows that the VGG19 model achieves a very high true positive rates even at extremely low false positive rates. An AUC of 0.999 indicates near perfect classification performance, far better than random guessing. Next, we have accuracy by model graph. The bar chart compares classification accuracy across different models, showing that VGG19, AlexNet, DenseNet, and BRNN plus GRU achieves the highest performance around 99%. BRNN and BRNN GRU flop perform slightly lower, while BRNN GRU flop ADA grade recovers near top accuracy. Next, we have precision by model graph. The chart shows that VGG19, AlexNet, DenseNet, and BRNN plus GRU achieve very high precision indicating few false positives. BRNN has the lowest precision, while the BRNN GRU flop ADA grade model improves precision back to near top performance. Next, we have recall graph. The graph compares recall scores across different ML models, showing that VGG19, DenseNet, and BRNN GRU flop ADA grade achieves the highest recall. BRNN and BRNN GRU flop has noticeably lower recall, indicating they miss more true positives than the other models. Next, we have F1 score by model graph. The graph shows that VGG19, DenseNet, BRNN plus GRU, and BRNN plus GRU flop ADA grade achieves the highest F1 scores, indicating strong overall classification performance. BRNN and BRNN GRU flop has comparatively low F1 scores, reflecting weaker balance between precision and recall. Next, we have 400x graphs. In this first, we have confusion matrix graph. The confusion matrix shows that VGG19 correctly classifies most samples with strong diagonal values, indicating high accuracy across all classes. Some misclassification occurs between similar tumor types, but overall class separation is effective. Next, we have ROC curve graph. This ROC plot shows BGG19 one versus rest classification performance, with most curves hugging the top left corner, indicating strong discrimination across all classes. High AEC values mean the model achieves high true positive rates with low false positive rates overall. Next, we have accuracy graph. This bar chart compares model accuracies showing BGG19 and AlexNet achieving the highest performance among all models. Hybrid and recurrent model performs moderately, while standalone BRNN based variant shows lower accuracy overall. Next, we have precision by model graph. This chart shows precision across models with VGG19 and AlexNet achieving the highest precision, indicating fewer false positives. BRNN based model, especially BRNN GRU plus flop, have much low precision, while adding ADA grade improves it noticeably. Next, we have recall by model graph. The graph compares recall scores of different ML models with VGG19 and AlexNet achieving the highest recall. BRNN based model generally shows lower recall, through performance improves when combined with GRU, flop, and ADA grade. Next, we have F1 score by model graph. The graph shows that BDD19 and AlexNet achieves the highest F1 scores, indicating the best overall balance between precision and recall. BRNN based model have lower F1 scores, but performance improves when enhanced with GRU, flop, and ADA grade. Now, let us check with detection graphs. In this detection graphs, we have binary class and multi-class. First, binary class. In this first, we have YOLO precision graph. The bar chart compares precision across YOLO versions like V5, V8, V9, and V11. YOLO V5 has the highest precision, while YOLO V11 shows the lowest among the four. Next, we have YOLO recall graph. The bar chart shows recall performance of different YOLO models like V5, V8, V9, and V11. YOLO V9 achieves the highest recall, while YOLO V11 has the lowest. Next, we have YOLO MAP score graph. The bar chart compares mean average precision across YOLO models V5, V8, V9, and V11. YOLO V8 and V9 shows the highest MAP, while YOLO V5 and YOLO V11 perform slightly lower. Next, multi-class graphs. In this first, we have YOLO precision graph. The bar chart compares the precision of different YOLO models, showing how accurately each model's positive detections are correct. YOLO V8 has the highest precision, followed by YOLO V5 and YOLO V9, and while YOLO V11 has the lowest. Next, we have YOLO recall graph. The graph shows the recall performance of different YOLO models, indicating how well each model detects all relevant objects. YOLO V5 and YOLO V9 achieves the highest recall, while YOLO V8 has the lowest and the YOLO V11 performs moderately. Next, we have YOLO MAP score graph. The chart compares the MAP of different YOLO models, reflecting overall detection performance. YOLO V5 achieves the highest MAP, followed by YOLO V8 and YOLO V9, while YOLO V11 shows the lowest performance. Next, click on sign out. So finally, This project demonstrates that integrating bidirectional recurrent neural network with deep feature extraction significantly enhances the multi-class classification of breast cancer histopathological images. By effectively capturing contextual and spatial dependencies within tissue patterns, the proposed approach improves diagnostic accuracy and robustness compared to convolutional methods. This inclusion of detection, explainability, and a web based interface further strengthens the practical applicability of the system. Overall, the proposed framework serves as a reliable and efficient computer aid tool to support early and accurate breast cancer diagnosis. So, this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.